Interpolation. Types of interpolators.
This is the fourth geostatistic course about Kriging and co-Kriging interpolation and mapping. With this course, you are going to learn the different types of Kriging interpolation: Ordinary Kriging, Universal Kriging, Regression Kriging, Kriging with external drift, and also Ordinary co-Kriging. In the previous lessons, we was working with Ordinary Kriging and also with Universal Kriging, and now we are working on the Regression Kriging. For this third lesson, we was already working with different parts. The part 0, it was about the introduction. The first part, it was about how to create a grid using a shapefile with R and QGIS. The second part, it was about ordinary least squares. The third part was about generalized least squares. The fourth part was about the overfitting with the generalized additive models. And the part number 5, it was about the regression kriging on two different models. One, it was the generalized additive models, and the other one, it was the generalized least squares. In today's lesson, we are going to see the last part for this third lesson related with regression kriging, and it's going to be this lesson over here. Today we are going to see the different types of interpolators, and we are going to use as example all the exercise that we was doing in this third lesson about regression kriging. Also, at the end, we are going to create a new deterministic model that in this case is going to be the thin plate spline interpolation, also known as a minimum curvature interpolation. I would like to talk about the different types of interpolators in order to answer this question: why the dataset has a different range than the raster interpolation results. What I want to say with this sentence? Well, if we take as example the first map that we created with the air quality index for ordinary kriging, we can see that the dataset, the range, in this case for the air quality index, goes from 10 to 174. But after doing the Kriging interpolation, what we have is a raster, is this raster over here that we call reverse transformation, okay? Then if we check the values for this raster that we can do here with a specific script, statistics, and it's going to be the raster layer statistics, then we can put the layer over here. We have just one band, and then we can run this script, double click here to open the results, and what we can see here is that the range for that raster goes from this value to this value, right? And this value, the minimum and the maximum, are different than the values that we have in our data set. I'm going to put again our data set here. Is this one. As you can see, it goes from 10 to 174, okay? But the results that we get, it goes from 10.06 to 173.5. These values are very, very close to the data set, but are not the same. And now we are going to see what is the reason of that. The interpolators can classify as an exact interpolator or inexact interpolator. The exact interpolator, the model that we get, has the same value as the data set. For example, in this case, the data set is the green dots. Then the model that we create with the exact interpolator has the same value as the sample location in that point, okay? It means that in this sample location, we have the green value, but the model in that point has the same value as the sample. And it happens for all the sample values, okay? But when we check the inexact interpolator, we don't have the same values, okay? We have the sample value is this one, but the model, the closest value that we have is this value over here, okay? Then in the exact interpolator, we have in the model the same values that we have in the sample at the same location. But for the inexact interpolator, we have a different value. We don't have the same value. And between the exact interpolator and the inexact interpolator, we have the smooth interpolator. And the smooth interpolator, what happens is that also in this model, we don't have the same value as the sample location, but we have a value that is pretty close, okay? That's because we add the term smooth here. But the smooth interpolator is a case of inexact interpolator, but the values that we have in the model are pretty close to the real values of the sample. Then the question is, ordinary Kriging is a exact interpolator or inexact interpolator, right? In this case, we was using ordinary Kriging, and what we can see is that the data set has different values than the final raster results, right? Even if we go here closer and we select one point, for example, this point, this one over here, okay, let's go to select the data set here. Let's go to click on this point over here, then we can see the results, right? And here for the air quality index, we have 174. Then when we check on the raster file, now we can check the pixel value. Then the pixel value here is 173.51. We can see that the value that we have at the data set is different than the value that we have at the pixel in the raster file. However, these differences between the data set and the raster file, it's not enough to indicate that the ordinary Kriging is not an exact interpolator in this case. It depends on the semivariogram. Then let me show you the semivariogram for this case. In this case, we was using the spherical model, and here we have the semivariogram, and at the y-axis we have the semivariance for the log 10 of the air quality index, and for the x-axis we have the lag distance in meters. And the important thing, in order to say if the ordinary Kriging is exact or inexact interpolator, it depends on the Nugget effect, okay? In this case, the Nugget effect is very, very close to zero, okay? And when we don't have any Nugget effect, when the Nugget effect is zero or is very close to zero, we can say that the Kriging interpolation, it is an exact interpolator. But when we have Nugget effect, the result that we are going to get is an inexact interpolator. It's going to be pretty smooth, right? But it's going to be an exact interpolator. Then in this case, if the Nugget effect is close to zero, why we don't have the same results here at the pixel value and also at the data set? And now we are going to see the reason of that with the next slide, is this one, okay? We have to know that the raster file is made with pixels, okay? We can see the pixels over here, is these squares over here, but also we can see the pixels when we make a zoom. It's difficult, right? Because it's the same color, but if we go to the limit, you are going to see the pixels are more clear. Even we can see what is the dimension of the pixels, right? We can go here, measure the pixel from here to here, is around 1,000 meters, right? And from here to here is another 1,000 meters. It's 1,000 by 1,000, right? That's the grid that we decided for this raster file. And when we are calculating the predictions using the ordinary Kriging with this grid, we calculate the prediction at the middle of the pixel, okay? But as you can see, the sample is not at the middle. There is some differences, right? This one is over here, but we made the prediction at the middle of the pixel. And that's the reason, because we have different values. If the sample is located exactly at the middle of the pixel, then we are going to have the same value when we don't have any Nugget effect, okay? But if we have Nugget effect, as we said previously, it's going to be an inexact interpolator and the values are going to be different. But if the Nugget effect is 0 or is very close to 0, then we need to have the same values, okay? Also, another scenario is when we are doing the raster file and we are doing the predictions at the nodes of the pixels, okay? In this case, we are now calculating the predictions at the center of the pixel because we are doing the calculation at the nodes. Then here for each node, we are going to have one value. And if the sample location is at the node connection, then we are going to have the same value. If no, it's going to be different. And that's what happened in this example, right? In this example, we calculated the prediction value at the middle of the pixel, okay? And that's the reason because we have one value here and a different value at the pixel location. As you can see in this case, it shows here the Nugget effect is 0.006. As I said, it's very close to 0, right? And another important concept related with the predictors is that the predictors can be local or general, right? When the predictor is local, it means that we are using the closest values, as you can see over here, the closest values to predict the value in the unsampled location, okay? What are the unsampled locations? Well, are all these pixels over here, right? Where we don't have any value. In this case, all the nodes are the unsampled locations that we want to predict the value, okay? And to predict that values, we can use an indicator that is local or an indicator that is general. When it's local, it means that we are using the closest neighbors to that location that we want to predict the value, okay? And that's what we are doing with Ordinary Kriging. In Ordinary Kriging, we are using the range to decide what neighbors we are going to take to do the prediction in that unsampled location, okay? In this example, what is the range? The range is this value over here in meters, right? Then we are going to use this range to know how long we are going to go in order to predict the values in the unsampled locations. But when we are using a general indicator, we are going to use all the samples to predict the values in the unsampled locations, okay? And that can be reflected also over here. Let me show you. Over here, right? Let's go to make this one smaller, okay? In the exact interpolator, it's pretty common to use a local interpolator, okay? And when the interpolator is inexact, in general, we are using all the samples, right? In this case, for example, to predict this value over here, that is an unsampled location, we are going to use all the samples, right? And in this case is, for example, a deterministic model that could be a first order polynomial, right? In order to create the model, we are using all the samples, okay? But for the Ordinary Kriging as an exact interpolator, we are using the range to predict these values over here or these values over here, right? And the range is what we saw over here. Is the distance from here to here, that's the range. Then if we want to predict, for example, this value over here, we are going to move all this circle over here, and then we are going to take just the samples inside the circle to predict the value over here. Now what we are going to do is to have a 3D visualization of the data set with the model in order to see the exact interpolator, okay? To do that one, we are going to use the QGIS, and we are going to use a specific plugin that is the QGIS 23JS, okay? We was talking about this plugin at the previous lesson. Then if you know how to use it, just check that lesson over there. Then click here to open. Then I'm going to take the background because I don't want to see the Google satellite image. And also we are going to do some modifications here. At the scene, we want an exaggeration of 250, for example. Apply in order to see the 3D effect. As you can see now, we can see the 3D effect. Before it was a flat one. Also, I want to, at the moment, take the data set. I don't want to see the data set. Then I'm going to take the data set, and also I want to do some modifications here. I want transparent, and this one is good, apply. But also I'm going to take the perimeter and the contis, okay? That one looks better. Now I'm going to make some modifications here. Properties. I want the absolute, but I want the circles smaller. 5,000, apply. Okay, and zoom to the layer. Oh, here maybe we have to properties. Here, select the parameter, right? Apply and okay. And as you can see, all the data set is contained in the plane, right? In the model. Some values could be a little bit higher than this one over here, right? But it is also because of the exaggeration, right? If we reduce the exaggeration, go to settings, here for example 150. Apply. That things are not going to be that evident, right? As you can see now, right? Then this model with the Kriging interpolation is what we can see over here in just 2 dimensions, right? Is this one over here, the exact interpolator. Here is in 2 dimensions, but here is in 3 dimensions. In this example, we can say that the ordinary Kriging is acting as an exact interpolator, or very close to the exact interpolator. And another example of an exact interpolator, it is the team, right? The team is known as a Triangulated Irregular Network. And if you go to the GeoRGB YouTube channel, here we have an example. Is this video over here when we was working on the Triangulated Irregular Network interpolation. Then here in this case, let me pass the ads. In this case also, it's a very good example about an exact interpolator. Then here we are going to create a raster file that is based on this interpolation. And with this interpolation, we are using just the closest neighbors to predict the values in those locations where we don't have any sample, okay? And this is an excellent example of exact interpolator, okay? Now I would like to show you another example, but in this case is going to be based on an inexact interpolator, okay? This one is the, let me show you over here. This one is the case based in 2D, but now we are going to see the case based in 3D. Remember, for the Wolfkampf aquifer data set, we predict a different type of trend surface. And in this case, what we can see over here is the first order trend surface associated with the ordinary least squares. Then we are going to see now this model in 3D, where we can see the model and also the data set. Then again, we are going to go to the plugin. And now we can load the surface, is this one. So to the layer, now we are going to do some modifications here. This one is the trend surface, maybe the exaggeration is too much. We can put 150. Okay, and also I would like to make some modifications here because I want to apply this one and I want to clip this digital elevation model with the perimeter number 2. All these things are explained at the previous lesson. Okay, apply. And also what I want is to take the, well, that one is good, but I'm going to take the data set. Okay, and I'm going to add the data set over here. And as you can see, now we have the model with the data set. And this is a very clear example of an inexact interpolator. Okay, it's a deterministic model, right? And is the different type of deterministic model that we was using. It was the first one, right? The ordinary least squares is this one, and is this model. And this case is also a very good example of a general interpolator, right? Because we are using all the data set to predict this model, right? And with this model, we can predict the unsampled locations, right? But we are using all the samples at the same time to create this surface. Now we are going to see another example, but in this case, it's going to be based on the second order trend surface. Then we are going to take this one out, the first order trend surface, and we are going to select the second order trend surface associated with the ordinary least squares. And then we are going to do the same, go to the plugin and click here. Then we can select the layer to be open, the second order trend surface from the ordinary least squares. And here what we have again is an inexact interpolator where we can see the model and with the data set that is quite far away from the model. The next example is going to be the second order trend surface associated with the generalized least squares. Then we can take this one out, go again to this one, take this one out, select the generalized least squares for the second order trend surface, and load again the 3D model. Then here we can select this one and go zoom to the layer. And as you can see, again, in this case, we have an inexact interpolator as the other examples. Then the next example I would like to see is an unsmooth interpolator. And to do that one, what we are going to do is to use the generalized additive models with 29 nuts. Remember that when we are using the generalized additive models, what we are doing is divide the data set in different sections according to the number of nuts. And for each section, what we are going to do is fit a thin spline, okay? Then as more sections we have, more splines we are going to fit in our data, right? And as bigger is the number of nuts, more local is going to be the fit, right? Because more sections we are going to have in our data set. Then again, we have to go here, take this one out, select the model associated with the generalized additive models with 29 nuts, and then we are going to see this 3D model. Then here, what we have to do here is select this one and leave the layer to be loaded. Let me see if that one is the proper one. Yeah, it is. And as you can see, in this case, the model is more close to the data. In this case, we have the 3D visualization, but here, this one over here is the 2D visualization, right? And the smooth interpolator is this example over here, right? Where the model, it's pretty close to the data, but it's not at the same location as we have with the exact interpolator. Remember that the generalized additive model is an inexact interpolator, but as it is pretty close to the data in that case, because we have a big number of nuts, we can say that in that case we have a smooth interpolator. But if we reduce too much the number of nuts, what we are going to have is a clear example of an inexact interpolator. Now what we can do here is to go here, take the generalized additive model with 29K and use the 10K. The 10K also is going to be a pretty smooth interpolator, okay? Because we divided the data set in 10 different sections and in 9 different sections, and we are going to have the model that is going to be pretty close also to the data. We can see that one. Let me load the 3D model here. Then we can take this one out. And now we can load the 10K over here. Then zoom to the layer. And in this case, as you can see again, the data, the model, it's pretty close to the data. If we compare this model with the model associated with the first order trend surface of the ordinary least squares, we can see the big difference, right? And the last example that I would like to see, it's a ordinary Kriging interpolation where we have an inexact interpolator, okay? Then what we are going to do again is take this one out, select the regression Kriging with the generalized least squares plus ordinary Kriging, this model over here, and let's go to see the 3D model of this one. Let's go to select over here, is this one. And here we have an example of ordinary Kriging with an inexact interpolator. Why? Because the residuals of the generalized least squares has some Nugget effect, and it is having some Nugget effect. We have an inexact interpolator. Now we are going to move on to the next topic. In this case, is going to be how to do the thin plate spline interpolation, known also as a minimum curvature interpolation. And to do that one, we are going to use the RStudio. I already opened RStudio and I added the file related with this thin plane spline regression interpolation, okay, for the groundwater flow direction of the Wolfcamp aquifer dataset. Now what we are going to do is just run all these lines. Then first we are going to load the libraries. In this case, we are going to use a new library that is the package fields. With this package, what we are going to do is the thin plate spline regression. Then I'm going to load the dataset and I'm going to create a backup of the dataset. In this dataset, what we have is the ID, the X and Y coordinates in UTM and the groundwater elevation in meters. As you can see, we have a total of 85 samples. And these samples are just the groundwater elevation inside of a piezometer. Then we can close this one. And in order to work with this package, what we need is to have the UTM coordinates in a matrix. Then we are going to run the next scripts. First, I'm going to create a vector indicating that the data frame has three different variables, x, y, and the groundwater elevation. The next thing I'm going to do with this new object is to create the matrix with the x and y coordinates. Then if we see the class of this new object, we are going to see that it is a matrix. Then with the structure, we can see this matrix. This matrix has just two columns with 85 samples. In each of these columns, we have the x and the y coordinate. With the next script is this one. What we are going to do is the regression associated with the thin plate spline, right? Is the interpolation. Then we are going to add the coordinates in a matrix, as we did over here, right? And also we are going to add the data set, this data set, indicating that what we want to use for the interpolation is the groundwater variable. This groundwater variable is this variable over here, right? The groundwater elevation. Then we can run this script here to do the interpolation. And now, if we press summary, you are going to see that here we have a lot of different parameters and a lot of different information. We are not going to talk about this information, but if you are interested in to use this kind of interpolation, you can run the help and see the mean of all these parameters over here with the help, right? Because there are too much information. I have to say that the field package, it's not very popular, right? Not a lot of people is using this package, and it is not easy to find tutorials on Google, right? When you are making your own search, you are going to see that there is not too much information related with this package, right? That is because it's not really popular. Sometimes it's difficult to work with packages that there is not too much information, right? To do your own investigation. If you compare, for example, this package, the fields, with the package that we was using previously with the generalized additive models, that it was the NGCV package. This one is very popular, and you can find a lot of information, a lot of tutorials, and it helps a lot, right? But for the field package, you are not going to find too much information, okay? And that's sometimes a big deal. Okay, now with the next line, what we are going to do is create a table where we are going to add the residual values and the predicted values associated with the interpolation that we did over here, right? Then we can create that table. We can run this one. Then with the next line, we are going to say that the residuals from this model, the thin plate splines, is equal to the residuals that we get over here in this object. This object is this object over here, okay? Then we can run this one. And if you now check this one, you are going to get the residual values, okay? The 85 residual values for each of the samples that we have, right? Then with the next script, we are going to add these residual values to this table over here, okay? Then we can run this one. And now we are going to do the same, but for the predicted values. Then we can run this one. And if you check this one over here, you are going to have the predicted values for the 85 piezometers, right? For the 85 samples. And now we are going to add these values to the table. And at the end, also what we are going to do is create a new field that is going to be the quality control, where the residual values plus the predicted values has to be equal to the groundwater elevation, right? Then we can run this line from here. and the next line also. Now we can see the table. We have the residual values, the predicted values, and the quality control. And as you can see, the quality control is equal to the groundwater elevation, has to be the same value. Then we can check some of them to make sure that everything is correct, okay? And everything looks good. Now we can close this table. And now what we are going to do, if you want to save this table in a spreadsheet, you can use this script over here. But what I'm going to do is just a histogram with the residual values. Now we are going to go to plots, and I have here the results. Here at the end, what we want is to have a normal distribution of the residuals, right? Where the median and the mean value be as closer as possible. And that's it, right? We want also a symmetric histogram without any outlier, things like that, okay? In this case, it's not that bad. I have to say that when I was doing the interpolation with this script over here, I use all the parameters by default, right? But if you want to play and make some modifications, you can check the help, see the parameters that you can use in order to make some modifications on the interpolation, okay? Then the next thing that I am going to do is to create the grid where we are going to predict the values in those locations where we don't have any sample, okay? But this grid is the same as we did for the ordinary least squares, for the generalized least squares, for the generalized additive models, okay? In all of them, we use the same grid, and in this case, it's going to be the same again. Then what I'm going to do is select all this grid, and I'm going to run all together, okay? Because if you want to see how is working this grid, you can check the previous lessons, right? Then at the end, if we go to plots, we created this grid. Now what I'm going to do is to use the interpolation that we did previously, this interpolation over here, this one over here, to predict the values at the center of each pixel. Remember that in this case, each pixel has a dimension of 500 by 500. Then we are here, and we can start to run these scripts. First, I'm going to create a backup with the grid with this name. Now I'm going to convert the grid as spatial point data frame. Now I'm going to assign the reference coordinate systems to the new grid. Now we can see a summary of the grid that we created. We have this information. At the moment, inside of the grid, we don't have anything, right? That's the information related with the ID, right? There is nothing inside here, right? And now what we are going to do is convert the grid in a matrix to work with the script predict Krig, okay? That script is from the field package. Then we can run the next lines. And now we can see a summary also. And now what we have is the X and the Y coordinates, but not much information. Then with the next script, we are going to do the prediction. To do the prediction inside the grid, we are going to use this script. And what we are using is the interpolation that we created at the beginning with the new grid. That is this grid over here. Then we can run this one. And now we can see a summary. And as you can see, now we have one new variable inside this grid that is called V1. This V1 is the predicted values, is the model, the deterministic model, okay? Then we can see also the structure. We can see the class, and we can make a view. Then with the next script, what we are going to create the grid with the predicted values as a spatial point data frame. And for the next script, convert the grid as spatial pixel data frame. Now, in order to improve the computational efficiency, we are going to do a full grid. And now we can check the statistics and characteristics of the new grid. Here you can see the dimensions of the cell, the number of cells that we have in the X and the Y rows and columns, and also the variable that we have inside the grid. Then with the next script, what we are going to do is plot this variable. That this variable is the predicted values, is the deterministic model, right? Then we can run this one and print the results. Then we can leave the software load the data. It takes a little bit of time. And here we have the results. Now we can maximize this screen over here. And what we have here is the thin plane spline regression interpolation, also known as a minimum curvature, okay? And here we have the scale for the groundwater elevation. Now we can move on to the next script. Convert the new grid a data frame in order to manipulate the variables, okay? Then we can run this one and view the table. And as you can see here, what we have is the variable located at the first column, right? Then we have X and Y. And we want to modify that one, and we want to put the column number 2 and number 3 first and second, and the column number 1 as a third column, okay? If you see here, what we want is to have this column over here, this column to be the first, and this column to be the second. Then to do that one, we are going to use this script. Now we can see the new grid is this one, X, Y, with the variable of interest, that is the deterministic model. Then create a raster with the new data set. Then we can run this one. And in this case, we are using the library raster, and we are going to create this object, and this object is going to be a raster. And in this raster, we are going to have the new grid where we predict the deterministic model. And with this script, we can plot the new object, that is this one, that is a raster file. Then we can run this one, and we can plot that one. If we want to see a full screen, we have to clean all these ones and run the plot again. And this one is the final result. This result is the same as this one. No, let me load this one. But in this case, we have the contour lines. And in the other case, we don't have any contour lines over here. Now with the next script, we can check where is our directory, because we want to know where is our directory in order to know where we are going to save the final raster, right? To be loaded on QGIS. Then with this one, we can see that our directory is this one. Then now we are going to export the trend surface. It's not, this one is not good. Export the trend surface according to the thin plane spline regression interpolation. Then we are going to save. And we are going to run this one. With the next script, we can see the files that we have in that folder. Don't worry about this one because the interpolation is good. And now we have the TIFF file that is the trend surface, is this one. Now we can go to QGIS. First, if you want, you can check the folder. Is this folder? I save in this folder. I open this one, and this one is the file I'm going to load in QGIS. Then go to QGIS here, and let's go to load that file. Then go here, and is this one, select this one, open, add, close, add the reference coordinate systems, that is this one. Okay, take this one out, because that one is the regression Kriging associated with the generalized least squares plus ordinary Kriging. We don't want to see this one. We want to see the new one, is this one. Then in this one, we can make some additions here. That is going to be this one here. This one is good. Equal intervals, 14 intervals. Apply. And I want to have something discrete to see the contour lines. Apply, and okay. And this map that we have here is the same as this map over here. In order to keep the same map, I put the 14 contour lines, right? And in that way we have the same one here and also here. Now, the next thing I want to do is to see the 3D interpretation of this model. Then again, we are going to go to Web, QGIS 3JS, and open this option. Then now we are going to select the trend surface with the thin plane spline regression. Is this one? Let's go to leave the software to lower the surface. And this one is the model. As you can see, in this case, we have another smooth interpolator, okay, where the model, the deterministic model, is pretty close to the data, okay. This case is something pretty similar at the results that we get with the generalized additive models. Then the next thing that we can do is to see the variogram analysis related with this deterministic model to see what's going on. Then we can run these lines. First, we are going to create a vector with the coordinates with this script. Then we are going to create the variogram. And now we can plot the variogram. And as you can see, this variogram, it's like opposite, right? Because, you know, what we have on the variogram is that the semivariance is increasing, right? But the semivariance here is decreasing. It is indicating that we don't have any spatial autocorrelation in these residuals, right? Even now we have a general view with 150,000 meters. But if we make some zoom on the 50,000 first meters over here, we are going to see clear that there is no spatial autocorrelation, right? And that's what we are going to do with the next script, right? But just to give you a summary of this information, we are going to create this object. We are going to do a variogram, and we are going to use the residuals from the table that we created previously, this table over here. And we are going to say that the residuals doesn't present any trend, okay? Because we remove the trend with the deterministic model, right? Because now we are working just with the residuals. Then with the next one, what we are doing is plot the results. Now with the next the script, we are going to do the same, but we are going to be focused on the 60,000 first meters over here until here approximately, right? In this case, we are assuming that it has to be the correlated area over here, right? But we know already that there is no correlation in these residuals. And also we are going to put a lag distance every 6,000 meters. Then we can run this one and we can plot the results. And as you can see, again, there is no spatial autocorrelation. Looks like a poor Nugget effect, right? Then we can try to fix a model. But as we are getting over here, there is no fitting models, right? Because there is no convergency after 200 iterations. But we can force something adding these values over here. And again, we can plot the model. With that one, we can see the results. Is these results over here, right? Then we have the spherical model. We have this partial seal with this nugget effect with this partial seal. As you can see, the nugget effect is bigger than the partial seal. And also we have this range, right? This value doesn't have any sense, right? But we force to fit a model on the data, and that's the results, right? And that's what we can see over here, right? That the nugget effect goes from here to here and is bigger than the partial seal, right? Then as a conclusion, we cannot use these residuals to do ordinary kriging, right? Because there is no spatial autocorrelation on the residuals. Well, that's the end of this lesson of regression kriging, and see you on the next lesson that is going to be about kriging with external drift.